Hi guys, in this video I'm going to talk about plotting tubes using the main unit normal and binormal vectors. I'm going to start with a really simple curve in three-dimensional space. I've got a circle of radius 2 that I've essentially just embedded into 3D. So technically this curve is three-dimensional because it's 2 cosine comma 2 sine comma 0, but it's a very simple three-dimensional curve. Now you guys know from my last video that we can define the unit tangent as the tangent vector divided by its own magnitude, and we could plot some of those unit tangent vectors if you're interested, so you can watch that move around the curve. Very reminiscent to what you saw in 2 dimensions in my previous video. Now if you want to throw in the main unit normal vector, that would be the derivative of the unit tangent vector divided by its own magnitude. And what's special about the main unit normal is that it's always perpendicular to this direction vector. So we could think of this vector as always pointing into the concavity of our curve, or we could think of it as always pointing towards the change in direction on our curve. Now I'm in three-dimensional space, so I can actually spice it up a little bit more. We can now take the cross product of the unit tangent vector and the main unit normal vector and get a new unit vector that's perpendicular to both unit tangent and main unit normal. We're going to name it the binormal vector. It's the cross product of unit tangent and main unit normal, and we can see what it looks like. Yeah, pretty cool. So now we have 3 mutually perpendicular unit vectors. Now what's kind of cool here is that main unit normal and binormal, since they're a pair of perpendicular unit vectors, if you think back to previous things that we've talked about, a pair of perpendicular unit vectors can be a nice way to define a plane. So we'll get a really nicely defined plane out of this. And that plane is special because any plane we plot using those 2 vectors is guaranteed to cut the curve perpendicularly because that plane is going to be perpendicular to the tangent vector. So take a look here. It's the same picture as before, but I threw in a piece of plane that basically has its starting point at P of t and its I and j vectors defined by main unit normal and binormal. Now, why would anybody want to go through this process? Well, there's some cool things that we can do with a plane like this, with our main unit normal and binormal. One thing that we can do is plot a tube. So look at this parameterization for this tube. So I've got a surface, m of st, so look at 2 parameters there, so it's a surface. M of st is equal to p of t plus cosine of s times main unit normal of t plus sine of s times binormal of t, where our parameters have some bounds there. And if you kind of dig into this equation, it's basically a starting point plus, now we have cosine and sine for a circle, and then main unit normal and binormal, those are essentially our I and j vectors for plotting our circle onto a plane. So it's basically a starting point plus cosine times I plus sine times j in a sense, and then as we let t vary along the whole length of our curve, that'll be a bunch of starting points with a bunch of different I and j vectors with a bunch of different circles. So that's what's going to give us that effect of getting a tube. If you compare the parameterization for a circle plotted onto a plane and a tube, you can see those similarities when you line those equations up. But in a sense, main unit normal and binormal are serving as our I and j vectors for our new plane that we keep getting as we traverse that curve. So let's do it. Let's plot a tube. I'm going to take this exact equation right here and I'm going to plot it. So let's run this code here and let's drag the slider and there we go. Look at this tube. Whoa, it's like a donut shape. Let's do it one more time because that was pretty cool. A little bit of lag there. I wonder if I press the play button if we'll get a better animation. No guarantees. Yeah, that's pretty good. Anyway, this tube actually has a name. It's called a torus. There's a lot of interesting uses of tori in higher level mathematics. So kind of cool that you get to use one in this course. And finally, if that was useful, you're welcome to stop the video now and move on to some of your try-it problems. But occasionally, I do get students that ask me why the unit tangent and the main normal are guaranteed to be perpendicular. And I thought maybe just kind of putting this at the end of the video would be a nice way to end the video. You don't actually need this proof for the course at all. You're never going to see it on a quiz or anything, but it is a question that I get fairly frequently, and so I wanted to put it somewhere where you could see it. So here's a quick little proof about why the unit tangent and the main normal vector are perpendicular to each other. The main thing to remember is that the unit tangent vector has a magnitude of 1. So I can write that the unit tangent vector has a magnitude of 1. Now I can unpack that definition for magnitude. That means the square root of the dot product of the unit tangent with itself is equal to 1. Now if I square both sides of that equation to get rid of that square root, I have the dot product of the unit tangent with itself is equal to 1, and I'm going to take the derivative of both sides of this equation. Now what makes this work is that we know that the derivative of a constant is equal to 0. So when we do this, when we take the derivative of both sides of the equation, the right side is going to become 0. And then the left side, we can use the product rule for dot products. And it's the same as the product rule that you guys know from your previous calculus courses. So derivative of the first times the second plus the first times the derivative of the second, where multiplication here is the dot product. Oh, well, these two terms are actually the same, so I can collect them up and say that I have 2 of these terms. Divide both sides of this equation by 2, and what did I get? Oh, the dot product of the unit tangent vector with the derivative of the unit tangent vector is equal to 0, but the derivative of the unit tangent vector is just defined to be the main normal. So that proves that the unit tangent and the main normal vector are perpendicular to each other, which by extension also means that the unit tangent vector and the main unit normal are perpendicular to each other. Anyway, I hope you guys enjoyed this video, and good luck on your try-it problems.